Dr. Carroll, and this video is about approximation algorithms. So here are some of the most famous NP-complete problems. And we need solutions to these problems to solve a wide variety of problems. So then, and if you're interested in these, make sure you check out my previous NP-complete problem. So my question is, which of these is it not important enough to have an efficient algorithm? They're all NP-complete. They all have very long runtimes, except for the smallest of inputs. So which ones do we just not need an efficient solution? That's right, none of them. So we have three main options to how to deal with this exponential runtime. So you could think your boss is saying, hey, I need you to do this. And you're like, oh, that problem's NP-complete. Well, option one is, are your inputs small enough that you can just run an exact algorithm and it's going to run in exponential time? Maybe, probably not. Can you develop a polynomial time algorithm if for your special situation, your niche in circumstances? Maybe. If not, neither of those first two are practical solutions, then the third option is to instead implement a near optimal solution and using approximation algorithm. Let's talk more about that last one. To be able to understand that, we need to know how close to the optimal solution are we going to get. And that's where the approximation ratio, rho of n, comes into play. What this does is it quantifies the difference between the optimal and the approximation as a ratio here. Now it does have the assumption that each solution has a positive cost. That fits most situations, so that's good. That's not very constraining. Some vocabulary terms to understand this better is we have C star, which is our optimal solution cost, whereas our approximate solution cost, we're going to use the notation of C to indicate that. So if we have a minimization problem, that means that C star is greater than 0, but less than or maybe even equal to C. So if it's a minimization problem, then we have the ratio of C over C star is less than or equal to rho of n, our approximation ratio. And there we have it. Now, what if we're not minimizing? What if we're maximizing? If we're maximizing, then the approximation cost is greater than 0, but less than or potentially equal to C star. In that case, we have the ratio C star divided by C is less than or equal to rho of n, and that's our approximation ratio. We can combine these together and simplify this by saying, well, it's the max of those two. And then that's less than or equal to our approximation ratio. So you often see it written this way. Given it's this ratio, we know some things about it. For example, it cannot be less than 1. Our solution cannot be better than the optimal. If it was, then we misunderstood what the optimal was, and we have a new optimal. So we say these algorithms that produce these results are rho of n approximation algorithms. And I'll give an example of one in just a minute. There is a subset of approximation algorithms which we call approximation schemes. And so if we have inputs of size n and a fixed epsilon, then what a scheme is a 1 plus epsilon approximation algorithm. So generally what happens if as our epsilon gets very small, that dramatically increases the runtime. As we get closer and closer to the optimal solution, it's going to take a lot more time. And that's not surprising because an optimal solution for these problems that we're talking about, NP-complete problems, have very long running times. And so if that wasn't true, then we had a polynomial time algorithm, then we've just proved P equals NP. Probably not going to do that. So we say subset of these, we say it's a polynomial time approximation scheme if it runs in time polynomial for n and for any set epsilon greater than 0. We say it's a fully polynomial time approximation scheme if it runs in time polynomial to n and any fixed 1 divided by epsilon greater than 0. Let's talk about an example of applying this. Let's use vertex cover. And just to refresh your memory, I'm going to go over what is vertex cover again. What we're trying to do is just determine a set of vertices such that every edge is adjacent to another set in the edge. Formally, what we say is that for an undirected graph G with vertices and edges, the vertex cover is a potential subset of vertices V prime such that every edge in the graph, that one of the two vertices at the edge, the ends of that edge, is in V prime. And so then we've covered all of the edges with vertices. Some examples of vertex cover could be if you needed to observe traffic on every single road, where would you place cameras at intersections so that you could see every road? In a network, where would you put code in? Where would you use routers to observe every bit of traffic from every connection? Very similar setup. We could also use this in social networks to understand who is the most influential people. And then we could also use it to find the smallest set for indices for a database as well. So lots of different applications. If we take a brute force approach to find all subsets of k and smaller, we're looking at a big O of n to the k. That's terrible. There are solutions that exist for 2 to the k times the set of vertices, and even better than that. This is a well-studied problem. So let's talk about our approximation. We're trying to minimize the set, and so we're looking at approximation ratio. And what I'm gonna show in just a minute is a solution that is guaranteed to be at worst twice the optimal set. That's how fast this approximation solution runs. Therefore, rho of n equals 2, or this is a 2 approximation solution to the vertex cover set. Let's jump into it. I thought it'd be helpful to just put it into some pseudocode here. Here's our vertex cover approximation, taking a graph, and notice we're going to return a set, the set of vertices. And so we're going to create that set, the very first thing. These vertex cover is our vertex cover. We're going to make a copy of the edges because we're going to go through and keep track of all of them and remove them one by one. So while there's still edges, you could think one of those applications, for example, you're trying to monitor traffic levels, and so you need to cover every road. Each road is an edge. We can get we can get any one of those edges, and that's the beauty of this algorithm. It doesn't depend on the ordering of edges for our guarantee. So we get an edge. Then for each of the two vertices attached to that edge, we add both of those to the vertex cover, each one in turn. And all of the edges adjacent to those vertices Well, they are covered as well, so we can remove those because they are covered. And that's it. Very simple, runs very quickly, and then we can return our vertex cover. Let's see what this would look like as we run it. So here we have a graph with A is connected to B, B is connected to C, C is connected to D and E, D is also connected to E, F, and G, and E and F are connected. So let's say we arbitrarily chose the edge between B and C. Now B and C are now in our vertex cover, and that means the edges adjacent to both B and C are covered. So then let's say the next edge we arbitrarily chose was EF. Then we would add E and F to our vertex cover and remove the edges that are adjacent to both E and F. Now the edge from C to E was already removed, but this is not an exact algorithm, but an approximation algorithm, so we have some redundancy there. Then let's say we arbitrarily chose, there's still edges that need to be covered, so we're going to choose the only last edge, DG, and we're going to add that to the vertex cover as well. So while the optimal vertex cover, which is shown in the bottom right here, is B, D, and E, a size of 3 vertices, this approximation algorithm, at least with this run through, comes with a solution of size 6, twice as large. But for large graphs, it runs much quicker. Let's talk about that. We talked just a minute ago about what a brute force or what a more optimized solution would be, but here this approximation vertex cover solution, using an adjacency list for E prime to our edge copy, that runs in order proportional to the sum of the vertices and edges. That is so much faster. If you think of a very large network, that makes a huge difference. Can you think of a better approximation algorithm for vertex cover? Let me know. Here's some other well-known NP-complete problems that have well-studied approximations for them. Thank you. I hope you enjoyed this video.